The next talk is by Jacob Fox on randomness intuition. Seems fundamental to the nature of the workshop.
Yes. So, right. So I proposed this title for the reason that I wasn't really sure what I wanted to talk about, and wasn't really sure if I wanted to speak. So it gave me the opportunity to talk about many possible things. Randomness intuition is indeed fundamental to the whole area. One can think of it as just renaming the probabilistic method, although I mean something a little bit more specific here, that you really understand the problem by considering a random object, and that's really essentially the right thing to look at. So randomness is very useful to understand many extremal problems in combinatorics, number theory, coding theory, many areas of mathematics. Some of the early example results from the 1940s, and these really changed how people think about problems. Instead of looking at very explicit constructions at the time, they thought from these examples that maybe we should start looking at random objects. So one classical example we've seen many times now is the ERDOS bound on Ramsey numbers. There are n-vertex graphs with no clique or independent set on 2 times log n vertices. You prove this by considering a random graph on n vertices. Shannon's theorem that there exist good codes, and there you consider a random code. And even earlier than these is a work of Zell where he showed that there are n-vertex tournaments with a large number of Hamiltonian paths. So a tournament is just a directed complete graph. A Hamiltonian path is a path going through all the vertices. And here it's directed, so you should, on that path, all the edges should be pointing forward. If you considered a particular path and you considered a random tournament, on that path it has a probability 1 over 2 to the n minus 1 that it's a directed path. And so in expectation, you'll get at least this many. And it took a long time, but eventually Noga alone showed that this bound is not so far off from the maximum possible. He gave an upper bound, which was in a factor n to the 3/2 of this. So the exponential constant 2 here is best possible. Okay. So today I'm going to talk about a variety of other problems where we see that looking at a random one gives essentially a best possible answer. So I'll start with an example in graph theory. There's an old conjecture of HAJOS, and I want to start with motivation for this conjecture. So if you have a graph G, the chromatic number is the minimum number of colors needed to properly color color G. So you assign each vertex a color, and you want no 2 adjacent vertices to receive the same color. And the clique number of a graph is the size of the largest clique. The size of a largest complete subgraph. And a very basic fact about graphs is that the chromatic number of a graph is at least its clique number, because if you properly color a graph, all of the vertices of a clique have to receive different colors. Now, the inequality is not true in the other direction. There are triangle-free graphs of arbitrarily large chromatic number. In fact, there's even graphs of large girth and large chromatic number. This is this old result of ERDOS. But much of, or a lot of famous problems in graph theory are about trying to prove partial converses of this fact. And one of them is the HAJOS conjecture. So instead of looking for a clique in a graph with a certain chromatic number, you'd like to say something a little bit weaker should still be there that looks like a clique, and that's a clique subdivision. So subdivision of a graph, so here's the complete graph on 4 vertices. A subdivision is you replace every edge of the graph by a path. And these vertices in the path are disjoint. So all the vertices you see are distinct. So you would replace every edge by some path, and you say nothing about its length. It could have no internal vertices, or it could have a lot. It doesn't matter. Okay, and the HAJOS conjecture says that if a graph contains no subdivision of kt plus 1, then it is t colorable. So instead of looking for a clique, you should be able to find, if the HAJOS conjecture was true, you should be able to find a large clique subdivision in the other direction. So this conjecture remained open for almost 20 years. It's a strengthening of Hadwiger's conjecture, which replaces subdivision by a weaker notion known as minor. And also the four-color theorem follows from the case t equals 4. So if you have a planar graph, it has no k5 subdivision, so it should be 4 colorable, if the HAJOS conjecture is true. For t equals 4. Now, the HAJOS conjecture in general was disproved by Catlin for t greater than or equal to 6, and that was a very specific counterexample he constructed. More shocking was that ERDOS-FAJTLOWICZ in 1981 showed that almost all graphs are counterexamples. So not only is it false, but it's really false. And what they showed is actually that you get, it's quite strong counterexample by considering a random graph. So sigma of G is going to denote the maximum T for which G contains a KT subdivision. And chi of G, again, is the chromatic number of G. So if you consider the random graph on n vertices, so for each edge you pick it with probability half, it almost surely satisfies that the chromatic number is on the order of n over log n, and yet the clique subdivision number is only root n. And that's much smaller than this n over log n. And the HAJOS conjecture was saying that sigma of G is at least chi of G. Okay, so let's disprove the HAJOS conjecture using this example. If you look at Gn1/2, the largest independent set it's going to have, just like in the proof of the bound on Ramsey numbers, it's only on the order of log n. So if you were to properly color Gn1/2, almost surely you'd have every color class is only going to have on the order of at most log n vertices. So you're going to have to use at least n over log n colors. So that shows that chi of G is at least on the order of n over log n. It also has the property that every subset that's bigger than essentially log n size has density about a half. And this is just by a simple union bound. So if you have a subset of size 3 root n of vertices from your graph, the number of pairs of vertices that are not adjacent inside is about half of the total number of pairs. If you had a clique subdivision of size 3 root n in your graph, you would pick out those vertices that are the vertices of the clique, and for each pair of them there has to be a path going between them. So the pairs that are adjacent you can just potentially use the edge, but the ones that are not adjacent you're going to have to use at least one internal vertex for. So you're going to have to add a vertex for each non-adjacent pair. Now the number of non-adjacent pairs we said is about half of the total number of pairs, which is 3 root n, choose 2, and this is bigger than n. So the number of internal vertices you're going to need to add is bigger than n. But your graph only has n vertices. And so you can't possibly put this in as a clique subdivision. So this is what ERDOS-FAJTLOWICZ observed. And they wanted to know how strong, how false is the HAJOS conjecture. So they introduced this function h of n. It's the maximum of chi of g divided by sigma of g over all n vertex graphs g. And so the HAJOS conjecture is just saying that h of n is 1. And the ERDOS-FAJTLOWICZ disproved this and showed actually it's at least essentially square root of n divided by log n. And they further conjectured that the random graph is essentially the strongest possible counterexample. So what does that mean? So not only is it a good counterexample, but it's essentially the strongest, that h of n is actually grows on the order of root n divided by log n. And this conjecture was proved a few years ago by Chungbom Lee, Benny Sudakov, and myself. I'm going to show you some of the ideas of the proof. One unfortunate aspect, we're not very careful about what's the c that we get as the upper bound. And we're not careful with that. We get a bound that shows that's at most 10 to the 250. Now actually, I now think that maybe a random graph, when you take p appropriately, so you take an ERDOS-Raney random graph g and p, you can figure out asymptotically what the chromatic number is going to be and what the clique subdivision number is going to be. And if you pick the right p-value to maximize that ratio, I think maybe that's actually the right answer for this problem. And so really it should be the case that the random graph is essentially the strongest possible counterexample. So I want to show you some of the ideas here. There's some nice probabilistic tools that go into it. The first thing is a reduction, though, to another problem. So instead of looking at chromatic number and clique subdivision, we reduce it down to a problem about the number of the independence number and clique subdivision number. So we work with this function fn alpha. So this result that I mentioned earlier, it follows from proving certain bounds on this fn alpha. It's the minimum of the clique subdivision number over all n vertex graphs with independence number alpha. So this is like a RAMSEY type question. If you think of G as your red graph, you'd like a clique subdivision of a certain size, or you'd like in the complement clique of order alpha. And we get certain bounds on fn alpha, certain lower bounds, depending on what alpha looks like. These bounds turn out to be tight in certain cases, we know. For alphas 2, the bound is fn2 is on the order of n to the 2/3. And this is tight for a specific example, which is there's these triangle-free graphs that no-go alone constructed, which are essentially as pseudorandom as possible. So the second largest eigenvalue is on the order of square root of the degree. It's a regular graph. And it has average degree, or all the vertices have degree on the order of n to the 2/3. And you can use that to show the fact that it's pseudorandom, you can use to show that the bound you get is tight. There should be similar pseudorandom KT-free graphs for t bigger than 3. We just don't know that they exist. So if you could prove they exist, it would follow that fn alpha is in fact on the order of this for alpha fixed. Another case where it's tight is when alpha is on the order of log n, and then you get a bound of square root of n. And that's tight for gn 1/2. So we know these bounds are tight in certain regimes. Let me say a little bit about the proof. There's several tools from graph theory and here. One of them is a very nice result in the area by Bolobash and Thomason and Komlosh and Samaretti. If you're in the dense case and you have enough edges, then you're going to have a KT subdivision just because you have enough edges. And so you can assume that the number of edges is not too many compared to the independence when you factor in the independence number. Then you have this graph. It's reasonably dense. So here's your graph. You have the vertex set. It's reasonably dense. This next lemma is an application of a technique called dependent random choice. It's a very powerful technique. Early versions of it were in works of Gowers and Rodel independently, and later Kostochka and Sudakov. And it's been a very useful tool to solve many old problems in extremal combinatorics. This particular version says that if you have a vertex set V, you can find, and you have a reasonably dense graph, you can find a large subset U of vertices, so that for every pair of vertices in U, you can find a large number of paths of length 4 between them that are internally vertex disjoint. And the way that you find this subset U is you take a random vertex of your graph and you essentially take U to be its neighborhood, and you show that it's with some extra work you can have it satisfy these. It'll satisfy these properties. Okay. So you first pass to this reasonably large subset. The next lemma shows that if you have this n-vertex graph and its independence number is alpha, there's going to be a fairly large vertex subset with few non-adjacent pairs. This is a very simple lemma. So if you have, if your whole graph doesn't have too many non-adjacent pairs, you can sample a subset of size S and it'll work. If it has a lot of non-adjacent pairs, and there's a vertex which has a lot of there's a lot of vertices non-adjacent to it, and you pass down to that neighborhood, the non-neighborhood of that vertex, and you just induct all the way down until you find a subset with this property. So if you're trying to build a KS subdivision, you would find this subset S within U with this property. And there's not so many non-adjacent pairs that you'd like to connect up. And for each of those non-adjacent pairs, you would just greedily take one of your paths that go outside to build it up. So your KS subdivision, so you'd find this subset of size S with few non-adjacent pairs. Your KS subdivision will only use edges of length 1 or length 4 here. Is there any questions about this? Okay, so that's what you do in the case that your graph is reasonably dense. This is just an overview of the proof. There's a lot of details that I'm not going over. And in the sparse case, you first pick out a maximum independent set. And here you're going to actually lose a constant factor in doing this. But what you like to do is pick out a maximum independent set, call it I. It's of size alpha. D is your density of your whole graph, but if you pass down to a large subset and lose a constant factor, you can assume that every vertex doesn't have too high degree. So you assume that every vertex has, in I, has at most dn neighbors. And then you can pass back the other way, and again lose a constant factor, which I'm not showing all the details of, and assume that every vertex outside in your graph has at most d times I neighbors inside. and inside this independent set. This is the maximum independent set that you pull out. And then again, in your graph G, you're going to, so here's your whole vertex that you pass again down to this nice subset U that helps you connect up pairs with short paths. So you have this U, and you also have your independent set I, and it's of size alpha. And this next lemma, it's borrowing an idea of Erdős and Szemerédi from 1972. It's not explicitly in their work, but this is essentially what they show, or some variant of this they show, is that you can find a large subset of U so that every independent set of that, so you can find a large subset W so that every independent set of W has order at most D times alpha. So you go down from independence number alpha down to D times alpha here. And the way you do that is each vertex has at most D times I neighbors in I. So you can, for each vertex, you can pick out a subset of size D times alpha, and you know its neighborhood is going to be in there. And the number of possible choices for these subsets of size T times alpha inside I is alpha choose D alpha. And so by the pigeonhole principle, there's going to be the size of U divided by this alpha choose D alpha vertices inside U that have their neighborhood inside alpha being amongst these D alpha vertices that you've picked out for those vertices. So you have this subset W, and its neighborhood inside alpha is contained in this little subset of size D alpha. Now, if W had an independent set of size greater than D alpha, you could add it to the rest of I except for its neighborhood here, this D alpha vertices you could throw out, and you would make a bigger independent set than you had in your whole graph to start with. And so that's a contradiction, and therefore the independence number inside W shrunk from alpha down to at most D times alpha by doing this. And that's helpful here. And then again, you apply the same lemma, except now you apply it with, instead of alpha, you have D alpha inside W. And you find your subset S inside W. So you've passed down using the density. OK. And it's the same idea. Is there any questions about this? Yeah.
Actually, I mean, you had earlier mentioned that this method of dependent random choices. Could you elaborate on that?
That would be another talk. But the basic thing is that if you wanted a set with the property that all small subsets, or almost all small subsets, have many common neighbors, you shouldn't just take a random subset in general. Because, so you have a dense graph, a reasonably dense graph, and you would like this property to have many common neighbors or many short paths. The problem could be your graph is a disjoint union of two cliques of size n over 2. This is a dense graph, and if you took a random subset, you'd just be cutting both of them in half typically. And if I took any two vertices, one from here and one from here, I can't get from one vertex to the other because the graph's disconnected. So what dependent random choice does is it picks a random vertex, and it shows it's very unlikely inside that neighborhood that you'll actually find these small subsets, pairs of vertices or some k-tuples that have few common neighbors. You're skewing away from that. Because if the subset's there, you would have to have picked one of its neighbors. And if it's few, it's unlikely that you would have picked one of its neighbors. So if you picked a random vertex here and looked at its neighborhood, it would work nicely here. And so that's the basic idea behind dependent random choice. And having this subset where every pair of vertices have many common neighbors or have many short paths, these sorts of things are very helpful for graph embedding problems. And there's some other related things like the Bolog-Szemerédi-Gowers theorem and additive combinatorics that uses this. So it's a very useful property. It seemed to be the missing ingredient, like here, for many problems. So that's how you would get this lemma up here. with this technique. There's a survey written on dependent random choice by Benny Sudakov and myself, and it's called Dependent Random Choice. And it goes over this in much more detail. Okay, good question. Any more questions? Okay, we'll continue. So I just want to point out a few conjectures. I think Fn alpha should be on the order of n to the alpha divided by 2 alpha minus 1. This is related to the existence of KT-free pseudo-random graphs that are as dense as possible that you could potentially get. And we just don't have good constructions, so it'd be very interesting. So we know it's true for alpha equals 2 because of Noga Alone's example of triangle-free pseudo-random graphs, but we don't know it in general. You can also, instead of having the number of vertices play a role, you can just ask, suppose a graph has chromatic number k, do you need to get a clique subdivision that's at least square root of k log k? So the HAJOS conjecture was going to replace this by k, and random graphs show that this should be maybe this should be the right answer here. You get a lower bound of square root of k by the Bolobosh Thomason and Komlosh-Samretti theorem that I briefly mentioned as a lemma on one of the slides. And so the big thing here is getting this extra log factor now. And I don't know how to get any beyond any constant here. And then, as I mentioned earlier, it'd be interesting to determine Hn asymptotically. Is it given by a particular GNP where you have to figure out what the right p-value is? There's a certain optimization question there which tells you what that p-value should be, which is not so hard to write down. Okay, so if there are no other questions, I'm going to move to another direction about multiplicity problems, and I'm going to talk all about finding lots of patterns. So Ramsey theory as a whole, you can summarize it as large systems contain patterns. And you'd like to have not just one of these patterns, but understand how many patterns there must be. So a natural question here is how many monochromatic copies of a graph H must there be in every two edge coloring of the complete graph on n vertices? So if you have a graph H and a number n, MHn is the minimum over all G which has n vertices of the number, minimum over all two edge colorings of the number of monochromatic, two edge colorings of Kn of the number of monochromatic H. And you can ask about the fraction of copies of H. So fraction, the minimum fraction, the same thing. So you look at all copies of H and you want to know what fraction of them must be monochromatic. If n is below the Ramsey number for H, there's a coloring with 0, so these two parameters will be 0 there, but once n is at least the Ramsey number, you have to have a monochromatic copy. You can show that CHN is monotonically increasing. And this is by a simple averaging argument. So CHN is at least CHN minus 1. You would average over all the Kn minus 1 subsets. And you can see that it's monotonically increasing. And so therefore, because it's somewhere between 0 and 1 and it's monotonically increasing, we know this limit exists, that C of H, which is the limit of CHN, n goes to infinity, exists. And the random bound gives us that C of H is less than or equal to 2 to the 1 minus m, where m is the number of edges of H. Okay. And the question is this correct? If you wanted to minimize the number of monochromatic copies of H, is it best just to consider a random one, and this asymptotically minimizes it? And this is what Erdős conjectured for cliques in 1962. And then almost 20 years later, Burr and Rosta thought it should be true for all graphs H. This still took a while. They're both false. So they say that random systems asymptotically minimize patterns in some sense. And Goodman's formula shows that it's true for triangles, and Thomason showed that it's false for K4, and in fact for every clique that's at least 4 vertices. And later work showed that it was false for all graphs that contain K4. So this conjecture is false. I think there still should be something that's not far off that's true. There's a few things that should be true that are of interest. So the one question is, for which H should it be true? And these are called common graphs. If C of H equals 2 to the 1 minus m, then H is called common. Otherwise, it's uncommon. This was bad terminology because almost all graphs are uncommon. But that was only discovered after the fact. So in the beginning, they thought all graphs were common. So it sounded reasonable in the beginning. Right, so when I was an undergrad, I found some examples which show that this can be pretty far off from the truth. So there's these things called lollipop graphs. In graph theory, we like to name things by what they look like. That should look straighter. This is a lollipop. You take a clique and you adjoin to it a path. And in this example, we'll take S to be on the order of t squared. The number of edges of this graph is t choose 2 plus essentially S, which is on the order of S. And the number of vertices is on the order of S in this graph. Now, this graph has chromatic number t, even though it has few edges. And what you can do, you can come up with a coloring where you give each color class, so blue is a disjoint union of cliques of order n over t minus 1. So that means, and the rest is red, so that means the red is a complete t minus 1 partite graph. So in red, which is the complement of blue, because it's t minus 1 partite, you won't have any copies of this H. So you get 0 red copies of H. So the blue copies, they all have to live inside. So blue is a disjoint union of cliques. Since blue is these disjoint union of cliques and H is connected, H has to fall inside one of these small cliques. And for each of them, you're losing a factor t minus 1 in the size. So for each vertex. So you're going to get a bound here of, for such a graph, you're going to get a bound here of C of H is less than or equal to t minus 1 to the minus the number of vertices of H. And when you do this computation out, you get in this example that it's m to the minus theta m. So a natural conjecture is that C of H should always be 2 to the minus 1 plus little o1. So this is saying this is 2 to the minus theta m log m as a upper bound on C of H. And I think the answer should be 1 here instead of something. It's very easy to put 2 here. And in joint work with David Conlin and Benny Sudakov, we threw the whole kitchen sink at this problem, and we could get 4/3 that we know. So combining dependent random choice and greedy embedding methods together, you can get this down to 4/3 as an exponent. The problem becomes very different when you add more colors. So once you have 3 colors, you can again take the lollipop graph. Instead of using the red graph being, so you have this red graph which was a complete t-1 partite. Now in red and blue you take a Ramsey graph without a KT clique in it. You blow that up, and inside each of those little parts you put a green clique, because you have 3 colors. And instead of having this t-1 now, you have exponential in t-1. So when you have 3 colors or more, you get that there exists H with C of H at most 2 to the minus m to the 3/2 up to a constant factor. And so you get much smaller out of this construction. For 3 colors, we can't get 3/2. We think for 3 and more colors, the exponent should be 3/2. But we can get 5/3 as an upper bound there. So at least something should be true along random for 2 colors here. Are there any questions about this? Okay. Continue. So a few years ago, so 2013, Hao Huang came and visited Chungbom Li and myself at MIT, and we were interested in looking at various multiplicity questions. In particular, we were looking at directed versions of these sorts of problems. And it's natural to count things within tournaments. So again, a tournament is a directed complete graph. And the natural analog of having a cliquer independent set in a tournament is a transitive, having a transitive subtournament. So a tournament is transitive if you can order its vertices so that all of its edges go forward. That's a transitive subtournament on 4 vertices. All the edges point forward. And you can look at analogous questions for tournament multiplicity. Let MKT be the number of transitive subtournaments of your tournament T of order K. And you can look at the fraction of subtournaments of order K and T which are transitive. Just as before, you can look at the minimum number of transitive subtournaments you could get over all tournaments on n vertices. So you want of order K. And this limit exists again because the CKN is monotonically increasing. And it's bounded between 0 and 1. And the random bound gives you C of k is at most k factorial times 2 to the minus k choose 2. And so we just started looking at this, and almost immediately we found a very simple proof that the random bound is tight. And it was so simple we just decided it must be folklore and didn't do anything about it. Then a couple years later, Corigliano and Razbarov, using the flag algebra machinery, posted a paper where they prove this, and they also show that for k at least 4, t is going to be quasi-random if and only if it has asymptotically the same number of transitive subtournaments of size k as the random tournament. So they're using the flag algebra machinery here. And I wanted to show our alternative proof. And just to see this, so let's say we were trying to count transitive subtournaments, including a vertex v in our tournament T. Well, v has an out neighborhood and an in neighborhood. And let's just count the transitive subtournaments where v is the first vertex of order k. So the number of those, well, you just have to look at its out neighborhood and find the transitive subtournaments of order k minus 1. So the number where v starts is going to be m of k minus 1, and I'm using n plus of v, the neighborhood of v, as the tournament induced on the neighborhood here. The same holds if you wanted to count where v is the last vertex. Except you have to look at the in neighborhood. N minus v. So you get mk minus 1 and inverse n minus of v, the in neighborhood, to count the ones where v is the last vertex. And if you sum this up over all vertices v in your tournament, you've counted every transitive subtournament twice, because you've counted it for its first vertex and its last vertex. You add it up. So that's a formula for the number of transitive subtournaments of order k in T. And by induction on k and convexity, you can show that you can get some particular lower bound from this. So just implying this by induction and on k, and you get this lower bound. This is going to be a convex function in that when n ends at least 2 to the k minus 1. And so it's minimized if at every step. So where would this come out? This would be the answer you would get if for every vertex it has the same in and out degree. And whenever you looked at an in neighborhood or out neighborhood, it also had this property, and it continued all the way through. Okay. So if you pick your first vertex, you then choices for that. That would be the case I equals 0. You could look at the second vertex. That would be the out neighborhood if that was exactly n minus 1 over 2. So the one thing I should have mentioned is the in neighborhood plus the out neighborhood is n minus 1 in size, right? Because this is all the vertices of your tournament. Okay. And then you can use this to get the second fact as well with a little bit more work. Now, I still think it's very interesting to look at these multiplicity questions in tournaments. So here we were just looking at the transitive subtournament. But you can ask similar questions for non-complete acyclic tournaments and look at these sorts of questions about when is the random bound tight, and there should be some general results in this area, similar to these common, uncommon results that we saw earlier. Okay. Is there any questions about this? Okay, now this common, uncommon is closely related to another problem known as Sidorenko's conjecture. It was independently discovered, this problem by ERDOS and Shimonovitz. So the general question is, how many copies of a graph H must there be in a graph with n vertices and m edges? This is a very basic question in extremal graph theory. There are many problems that can be phrased along these lines. When m is large, so it's on the order of n squared, so your graph is dense, there's this very nice conjecture of Sidorenko and ERDOS and Shimonovitz that if H is bipartite, the random graph with edge density P has an expectation asymptotically the minimum number of copies of H over all graphs of the same order and edge density. And this is known for a long time now for trees, complete bipartite graphs, even cycles, and then in more recent times by cubes by Hatami. And it has connections to a bunch of different areas. This problem came up quite naturally in other areas where you look at matrix inequalities and other questions in these areas. There's a very clean homomorphism version of this. So instead of actually counting full subgraphs, it's cleaner to count the number of homomorphisms from H to G. So these are mappings that are not necessarily one-to-one. It's just you map the vertices of H to the vertices of G, and you want to know what fraction of those mappings map all the edges of H to edges of G. And that's this TH of G. And in this version, the Sidorenko's conjecture says that TH of G is at least essentially the edge density to the number of edges of H. And this is what you would be getting for a random graph. There's also a nice analytic version of this where you can instead of taking a finite discrete graph, you can look at these functions on 0, 1 squared, and you can state it as an integral inequality. Essentially, these functions are now, these are essentially graph limits, and so it's very natural that it would have this analytic formulation. Although this analytic formulation, Sidorenko had posed in the 80s as an equivalent version. So it's something that maybe predicted the whole development of these analytic tools that we now look at in extremal graph theory. And these particular integrals come up in a bunch of different areas of physics and chemistry. So they're quite natural to look at. And we've seen earlier many different notions of quasi-random graphs. And one version is that the local counts are all correct. But we know this is equivalent to many other notions like discrepancy. One of the, well, it was surprising, but now we've seen this several times here, that quasi-randomness follows from this just for knowing it for edges in C4. And so we had this nice talk earlier by Matthias Schack, where he was looking at other pairs besides K2 and C4 and discussing which of those pairs imply quasi-randomness. And so a graph is p-forcing if this implies quasi-randomness. The density condition for K2 and F implies quasi-randomness, and it's forcing if it is p-forcing for all p. And Chung, Graham, and Wilson asked which graphs are forcing, and they showed that even cycles are forcing, and Skokin and Tama showed that complete bipartite graphs are forcing, and this all led in the direction that to the following conjecture: a graph is forcing if and only if it is bipartite and contains a cycle. So it necessarily needs to be bipartite. There's some simple constructions for that. And it also has to contain a cycle. So if your graph contains no cycle, it's a forest. And if you take a regular graph of edge density p, it didn't matter, so just every vertex has the same degree essentially. The counts are essentially the same for any particular forest because you can embed the vertices one at a time looking at just neighbors of the previous ones. And so the counts only depends on the fact that it's regular, and there's regular graphs which are not quasi-random. So this provides a stronger stability result for Sidorenko's conjecture that you only have tightness if your graph is quasi-random. In the language of graph limits, this is all very natural now that random graphs would give you optimal things. They're just the constant functions. If you look from the perspective of graph limits, they're very simple functions. So there's Sidorenko's conjecture, and a theorem by David Conlon and myself is that it holds for every bipartite graph H which has a vertex complete to the other part. And it holds for, so this is a large class of graphs. You have a bipartite graph, you just need to guarantee that one vertex is complete to the other side. The other edges can go however you like. Then you know Sidorenko's conjecture holds. And you get an approximate version for all graphs. So if you have an H that doesn't have this property, you can just fill in the extra edges out of one vertex and apply the fact that we know Sidorenko's for that graph and get a bound which is pretty close to the bound you get with the conjectured bound. And further, you get the forcing conjecture for every bipartite graph which has two vertices and one part complete to the other part. So the forcing conjecture also holds for a large class of graphs, and there's been a huge amount of recent work on extending this further by Lee and Segedy and Kim Lee Lee, Conlon, Kim Lee Lee. There's been a bunch of work since then. And there's two basic tools that they're using plus some additional ideas. The one thing that was really essential for our work is the use of dependent random choice plus a little tensor power trick at the end. But also, Lee and Segedy introduced these entropy inequalities, which is an alternative way of proving some of the same results. And seems to be able to prove a little bit more, too. So I want to turn our attention in the remaining 10 minutes to arithmetic versions of these questions. Are there any questions about the graph world before we move on to arithmetic type analogs of these questions? Okay. So we're going to let L be a linear homogeneous equation in k variables. Our coefficients, AIs, are elements of FP for some finite field FP. L is called common if a random two-coloring of FP to the n has asymptotically the minimum number of monochromatic solutions to L. And you'd like to know what are the common linear homogeneous equations. And this question and many similar multiplicity questions were looked at by Saad and Wolf, and they proved a lot of interesting results here. They showed that if L has an odd number of variables, so k is odd, then it is common. So that's a sufficient condition for it to be common. And so there's a lot of them, and there's a short proof of this. You could further look at analogs of Sidorenko's conjecture. And so you'd call L Sidorenko if every subset of Fp to the n with density alpha has density of solutions to L, at least alpha to the number of variables minus little o1. And this is the bound you'd get from considering a random subset of density alpha. And so they had an exact conjecture about what the Sidorenko linear equations are. This is actually quite natural. So if you could write your equation, say it has 2k variables, as you could split it up into two sides, and on each side you had the same thing written. Then it's not.
They're different variables.
They're normally different variables. I'm looking at the special case that they're actually the same variable, and I'm going to show that they're. So there's an equal sign here, and there's. I just brought over all the, in your version, the negative variables over to the other side. So you can think of all the. Okay, I'm looking at a very special equation here.
This is very special.
This is very special. Yes, I picked one linear form, and I just wanted.
The second row should be like
Ah, thank you. K plus 1. Thank you. I understand. Yeah. Yes. Thank you, Julia. Yes, these should be indeed different variables. There's 2k variables here. Thank you, Julia. Right. So yes. So this equation is Sidorenko for a pretty simple reason. If you look at each number m and look at how many times it's represented as the first linear form, the number of solutions to this equation would be summing up the square of that number over all m. So if you represent a number m in some number of ways, then you can solve this equation in m squared way, in that number of representations squared ways for that particular m. And then you just sum up over all m. And from the Cauchy-Schwarz inequality, you end up getting that this is going to be minimized essentially when you're random, when all of the m have the same number of representations as this side. So they observed that this is that equations like this are indeed so equations of this form are Sidorenko, and they conjectured that that's it. So that was recently. So you can prove pretty easily, actually, if you have an odd number of variables, it's not Sidorenko. And then when it has an even number of variables, so that's what this is essentially saying here. You can pair them up. You find some coefficient, and there's another coefficient that's negative of that, and you can pair those up. You can pair up all of your coefficients, and that's the only condition for it to be Sidorenko. And so you need to find some construction that works, and you can, and so in some recent joint work that Yufei Zhao and Hui Pham and myself were working around these sorts of arithmetic questions, and this, and Yufei had the observation of coming up with a construction using Fourier analysis. So actually looking at the Fourier coefficients instead of actually determining whether your element is in the set or not. Let's first look at the Fourier coefficients, figure out what the Fourier coefficients should be, because you can get counting from that, and then make the Fourier coefficients so that you actually can go back and get a set with this property. And so this conjecture holds, and also you can determine which ones are common, which linear equations are common. So if you have a linear homogeneous equation, it's if it has an odd number of variables, we know it's common by the Sod-Wolf result. If it has an even number of variables, the construction further shows that it's, and it's not of this form, the construction further shows that it's uncommon. And if it is of this form by convexity, you get that it's common. So it determines the common linear equations, and it seems a very interesting question to understand what about general linear systems of equations. And so in the Sod-Wolf result paper, they come up with a lot of interesting examples of uncommon systems of linear equations, and it's interesting to look at this more. And I don't have any good conjecture for the answer. Yeah, or general conjectures. Any questions about this? So,
just a remark.
Yeah.
The theorem
yeah.
is a one-line proof that was in a previous paper by Sierra and Senna.
Okay. I know it's basically one or two lines, but right, I didn't know that it was in previous work. Sorry. Thank you. So for arithmetic progressions, it's not the case that it's Sidorenko. So the equation x plus z equals 2y, but you'd still like to salvage this idea. So if you have a random subset of density alpha, the density of three-term progressions is going to be alpha cubed. And there are these subsets of density alpha that have fewer than that. If you take this Edel construction of f3 to the n, a subset of f3 to the n, you can use that to get, without any three-term progression. It's pretty dense. You can blow that up and get a construction with density alpha and only alpha to the 4.63 roughly density of three-term progression. So you can get very much fewer, but Ben Green showed that there's going to be some common difference. There's going to be some d, so that the arithmetic progressions of common difference d, you get density essentially alpha cubed. You get the random bound. And that's going to be best possible. You can't get beyond there for a common difference. Again, by considering a random subset, the three-term progression density and for all possible d with a particular common difference, they're all going to be concentrated around alpha cubed. So Green's theorem says if you have an abelian group, there's going to be an n of epsilon, so that whenever you take a subset of the abelian group of density alpha, there's a non-zero d, such that the density of three-term arithmetic progressions with common difference d is at least alpha cubed minus epsilon. So you can get essentially the random bound for a particular common difference, but you can't get it averaging overall. And it's a very nice application of arithmetic regularity. Recently, with Yufei Zhao and Hui Pham, first with Hui Pham for the case G is a vector space over a finite field, and then more later with Zhao for general abelian groups, we showed that this function grows like a tower. So you're using the arithmetic regularity lemma and the Green's proof, it gives a upper bound, which is a tower of height polynomial in 1 over epsilon. And we studied it more carefully. We improved the upper bound to logarithmic in 1 over epsilon tower height. And we have matching construction, which shows that it is tower type. And one thing that's very interesting is it's the first real application I see of regularity where you really need these bounds, these tower type estimates that come from it. So we know for a long time now that in these regularity lemmas, they require this tower type bound. But for the applications, we thought we always could get better bounds. And so this shows that that's not true. And it's interesting to explore when these regularity bounds are actually necessary further. Now, if you just wanted half the random bound, and so you wanted, for some common difference d, at least alpha cubed over 2. So before I mention that, why is the tower height logarithmic? You go through the proof of the regularity lemma, something like that. Instead, you look at the mean cube density at each step of your process. Instead of some additive term, at each step, the mean cube density goes up by a factor 2. And you only get logarithmically many steps in this process. So usually you look at the average of the square density. And for counting arithmetic progressions, it should be cube. And if you wanted to look at linear equations with k variables, it should be the kth power. And there's a good reason for that. Right, so if you wanted half the density, then you get a tower height which is on the order of log p times log 1 over alpha. So this is an fp to the n. And the log for the upper bound comes from the fact that you can get a better density increment at each step. So the mean cube density actually goes up by a power at each step. And that only requires log steps to finish off. And it uses in the upper bound an application of the arithmetic removal lemma. That was some joint work with Laszlo Mikuláš Lovász. And so you apply that within each step to get this better density increment. And then there's a matching lower bound construction. And it's very closely tied to the bounds in Roth's theorem for fp to the n. So I'll finish with just mentioning that there's also monochromatic versions of this. So you would like, so if you color with R colors, f3 to the n, you want to show that there's a non-zero d such that the density of monochromatic 3-term arithmetic progressions with common difference d is at least 1 over r squared minus epsilon. So there's going to be some d if your n is large enough. And for r equals 2, this follows from the fact that 3-term progression equation is common. But for r equals 3, there's no nice formula for the number of 3-term progressions. For r equals 2, there's a nice formula based on the set density of each color class for the number of 3-term progressions. But when the number of colors is bigger than 2, there's no such formula. And when you have 2 colors from just on average, you get the right number of 3-term progressions. It's not hard to show that this is logarithmic in 1 over epsilon, but when r is bigger than 2, it jumps to tower type for the same sorts of reasons, but the construction's a bit harder to do in the beginning. I've run a little over time. Thank you.
Questions? Okay.
Thank you.